All right, Ninja Nerds, what we're going to do in this video is we're going to talk about alcohol reactions, ether reactions, and some epoxide reactions. So, substitution of alcohols. All right, so here's kind of a general structure of what we'd expect an alcohol to look like, right? So I could draw any different type of alcohol. I'm just going to put the first one that comes to my mind, right? So I like, I'm going to go ahead and do cyclohexane here with a alcohol. So it's no longer cyclohexane, it's called cyclohexanol, right? So what I'm going to do is I'm going to take this alcohol and I'm going to react this alcohol with a specific reagent. So I could have talked about a lot of these, but we're going to focus on two main ones. One of the ones we're going to look at is we're going to look at PBr3 when we react this with pyridine. So pyridine. Okay, so we got two different things that we're going to use in this reaction. Before I even get into the mechanism of this reaction, because we're going to look at the mechanisms of these reactions, because that's how we're going to really understand organic chemistry. Because a lot of these reactions are going to have the same constant mechanism that you're going to see over and over and over again. All right, so first off, let's take a look at this alcohol. If I were to take a look at this alcohol, so pretend I put my hand over that alcohol, and I look at the carbon that the alcohol's binding to, right? That carbon is bound to two other carbons besides the alcohol, and it's bound to one hydrogen. So we say whenever a carbon that's bound to the alcohol is only bound to two adjacent carbons and one hydrogen, this is a secondary alcohol. Okay, this is a secondary alcohol. This reaction for PBr3 and pyridine can only occur when you have a primary and secondary alcohol. Okay, so now that we know that this can only occur when we have a primary and secondary alcohol, let's go ahead and dive right into the mechanism. Okay, so I'm going to kind of redraw this molecule here. And I'm even going to be a little bit more specific, and I'm going to put that alcohol on a wedge. And the reason why I'm going to put it on a wedge is because there is some stereochemistry in this mechanism here, okay? So a wedge just means that instead of it being in the plane of the actual whiteboard here, it's going to be poking out at you, okay? So we got this alcohol here. Let's react this with our PBr3. So there's our bromine there, a bromine there, and a bromine there with a lone pair of electrons. Okay, so now what happens here? These lone pair of electrons in the oxygen are going to love to attack that phosphorus right there. So it comes in and it attacks the phosphorus, right? So when it attacks the phosphorus, one of these bonds here between the phosphorus and the bromine breaks off. So phosphorus is like, hey, bromine, alcohol's coming to bind. I don't want you anymore. You leave. So bromine leaves, okay? Now what does that give us? Okay, so that's the first step of the mechanism. So now look what we have here now. So now after that reaction, we have the alcohol still on the wedge. It's bound to a hydrogen with a lone pair of electrons and a positive charge. Why? Because it's also bound to this phosphorus over here with the Br and the Br right there, right? With a lone pair of electrons. Okay, now what happens here? Another thing that happens here is that we have to get rid of this hydrogen. So we have to deprotonate this guy and get rid of this hydrogen. So now what we're going to do is we're going to react this molecule with a very good base called pyridine. If you remember, I put pyridine up there. Pyridine is a very good base. What does bases do? They love to react with these hydrogens and rip those hydrogens off because this nitrogen is a good nucleophile. So he's going to come in, rip that hydrogen off, and that's going to break down onto the oxygen. Then what do we get out of this? Out of that, let's come down here for this part here. Now we're going to have this guy here with still the same thing, oxygen bound to, no hydrogen there anymore, got the lone pairs, and now we're going to have the phosphorus with the two bromines. Now we got a good leaving group. We have a very good leaving group because this phosphorus and this oxygen, all these guys are pulling away from the ring, right? So they have a more electronegativity. So it's like exhibiting this electron withdrawing effect. When they have this electron withdrawing effect and they're pulling the electrons away from that carbon, it makes that carbon partially positive. So now we have a partially positive carbon. Remember that bromine that we kicked off before? He's still pissed that we knocked him out. So guess what he's going to do? He's like, all right, you guys want to do that to me? I'm going to take what I need. So he comes in and he does a backside attack. So imagine this oxygen's poking out in front of you. The bromine comes from the backside, gives him a little sneak attack, bang. And when the bromine attaches in, he's going to be coming into the plane of the blackboard. So he's going to be going in this way. So if you think about that, that's why I drew that wedge, because now look at the bromine. So if he comes in and attaches there, this bond here has to break off. So then what do we get out of this? We get a new bond formed. What did we do? All this was a substitution reaction, right? So all we did was substitute, instead of the OH, we put a bromine there. So what would the single step reaction look like if I were to run this? It's a simple one, right? But we put this on the wedge. So now if it's an SN2 reaction, and we'll talk about that in future videos, it means that two molecules are involved in the rate determining step. It means that it's attacking at the same time the leaving group's leaving. So it produces an inversion of the stereocenter. So there's our inverted stereocenter there. Okay, so that's our first substitution reaction. Not too bad. The second substitution reaction is going to be the same exact thing. Let's do this one in black. Okay, second substitution. Let's do the same thing. And let's put our alcohol here, and let's put them back on the wedge again. And now what we're going to do is we're going to react this alcohol with what's called SOCl2. Okay, so S, double bond, oxygen, Cl, Cl, and then what do we have here? The lone pair of electrons in the oxygen, what did it do to the phosphorus before? It attacked the central atom. Guess what? It's going to do the same thing. Attack that central atom. When it attacks the central atom, these pi electrons up here are going to come up onto the oxygen, because we don't want to have sulfur to have too many bonds. So then it kicks up onto the oxygen, and then look what we get out of this. So that's the first step of the mechanism. So then after that, our oxygen is still attached to that hydrogen with the lone pair of electrons and the positive charge, but now it's attached to a sulfur with a single bond oxygen, negative charge, and then it's bound to these two chlorine atoms. All right, now this is where it gets good, right? Remember the pyridine came and attacked that hydrogen before? Guess what? He's going to do the same thing. So the pyridine comes back. All right, well, in this case, he doesn't come back. He's just now coming into this reaction. He comes in, rips that hydrogen off, and guess what? Same thing as before, the electrons flop onto the oxygen. One other thing happens. These electrons that we put up on the oxygen are really, really high energy. We don't want it to be that high energy. We want it to come back down to low energy. So what happens is when they go up, they come right back down. And guess what? Sulfur says, I have too many bonds, chlorine. So I had to deal with oxygen. I'm going to have to let you go. So guess what? Chlorine leaves. Okay? Then what do we get out of this? So that was our second step of the mechanism. Now we have this guy here. Still have this bond here with the oxygen, but we lost the hydrogen, lone pair of electrons, sulfur, double bond oxygen, and one Cl here. Now what happens? Here's where it gets kind of funky. The chlorine that left, right? What he can do is he can do something kind of really weird here. That chlorine can come back in and attack. But when he attacks at the same side that the oxygen is leaving. So whenever the oxygen is leaving, that chlorine is going to come in and attack. So it's going to proceed. So whenever this whole leaving group's leaving, it creates a point where the actual nucleophile could attack from the front or the back, which produces what's called a racemic mixture. So it can have an inverted stereocenter or keep the same stereocenter. But in this case, it's really, really funky, because chlorine, when he attacks, he only forms the retained stereocenter. So what would be the result of this reaction? If chlorine comes in and attacks that carbon, what do we get? We're going to have the same stereocenter. So it's still going to be on the wedge, but now instead of it having this whole group here, what are we going to have? A chlorine. So how would I write this single step reaction? This single step reaction, if I were to squeeze it in up here, would just be like this. I'd have my cyclohexanol was on the wedge, react this with SOCl2 and pyridine. And when I do that, what do I get? I get my halogen, which was the Cl, but in this case, it's not going to be on the dashed line, it's going to be on the wedge. So it retains the stereocenter. Okay, so that's our substitution reaction. So we've just now, if I were to box this out right here, we have just talked about what? Our substitution reactions. So this was the first thing that we talked about. So we can check that off. We did the substitution reactions. All right, so now we've done the substitution, let's get into the protection of alcohols. Let's say here I have an alcohol, and I have on this, I have a double bond oxygen. And I want to do something to the double bond oxygen, but I don't want it to react with the alcohol. That's not a good, so we have to be able to do something to prevent this alcohol with reacting with the same reagents that's going to try to react with the aldehyde. So what we do is we put something on that to protect it and keep it from being reactive so that this reaction can actually occur. And we'll see that in the synthesis reactions. So what can we use in this? One of the things that they use is they use what's called TMSCl, which stands for chloro-trimethylsilane, okay? And what happens here is you're going to run this reaction and it converts it into something like this. And we'll see the mechanism here. I'm going to put TMS, and you'll see exactly what I mean here in a second. But then what we could do, we could go and react this, this aldehyde, and maybe we do an oxidation reaction with the aldehyde and turn it into a carboxylic acid, but we keep the alcohol from being oxidized. So that's the whole purpose of protecting it. So let's go ahead and dive right into the mechanism. Nothing crazy for this one. It's actually pretty simple. So we have those lone pair of electrons in the oxygen, same thing as before. Our central atom is silicon, and we have trimethyl, so 1, 2, 3, and we have a chlorine. The lone pair of electrons on them. What happens? Oxygen attacks the silicon, and this bond right here between the silicon and the chlorine breaks off. And then what do you get? Well, your first step right there, let's actually come down here. What do we get out of this? We get still double bond there. And then we have the oxygen with the hydrogen, lone pair of electrons over here with a positive charge. Then we have the silicon with the 3 methyl groups here. Now what can we do? Remember the guy who comes in and pulls off that hydrogen? He's back, pyridine. So now we have pyridine. And what can pyridine do? Pyridine can come in there and be like, all right, taking this back, buddy, need this, and rips off that hydrogen. Then what do we get? Well, then we have our protected alcohol. Because you'll see here that now we have the perfect protecting group here that can keep this alcohol from being reactive while we run another reaction on the aldehyde. And that is, so the TMS that I drew up there, the OTMS, that's just your trimethylsilane there. Whereas before we had a chloro-trimethylsilane. Okay? So that's our protection of an alcohol. Another reaction that we can run, it doesn't protect an alcohol. I want to mention this one because it's pretty bulky, just like this silicon, this chloro-trimethylsilane. But it's a really good leaving group. So I'm going to explain that real quick. But before I do that, I could actually reverse this reaction and go back to an alcohol. If I reverse this reaction and go back to an alcohol, because what if I want to deprotect it? All you have to do to deprotect this is react this with acid. So I'm going to react it with hydrochloric acid. And if I react this with hydrochloric acid, what it will do is it will put the hydrogen back onto the oxygen and put the chlorine back onto the silicon. And then what do I get out of this? I deprotect my alcohol and reform the chloro-trimethylsilane. Okay, so that's how I could actually deprotect it. So we protected it and then we deprotected it. Now let's go ahead and do a good leaving group structure. So some people think he's a very good protecting group, but he's really a better leaving group. He's a really, really good leaving group. So now what we're going to do is we're going to take a look here at reacting an alcohol with what's called a tosyl chloride. So let's say here I take my alcohol, same alcohol. I just won't put the aldehyde in there now. And I'm going to react with what's called tosyl chloride. So what tosyl chloride looks like, he's a pretty big fricker. He looks kind of like this. And you have your sulfur group here and a chlorine. So what happens? Lone pair of electrons in the oxygen love to attack the sulfur. And then this bond between the sulfur and the chlorine breaks off. What do you get out of this? That's the first step of the mechanism. You're going to notice it's a constant similar trend over and over and over again. That's why these mechanisms aren't really that hard. So then, boom, 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 with our methyl group there. Now what do? You remember from before. We reacted with pyridine. And what happens with the pyridine? The pyridine comes over, rips off the hydrogen, and plops that bond right there, right? The lone pair of electrons. That was the second step. And then what do you have here? Now you have a oxygen there with your, I'm going to name this thing now because it's no longer called a tosyl chloride anymore. It's actually called a tosylate ester. So this right here, if you look here with this oxygen and all this tosyl group over here, because this is your tosyl group, this is just your oxygen right there. When I combine the tosyl group with the oxygen, I form what's called a tosylate ester. A tosylate ester. Okay? So now I've formed a very, very good leaving group. This is such a good leaving group that if you react this with any other reaction, it's going to want to leave very, very easily, which you can do another substitution reaction that we talked about before. Okay? So that's a very good leaving group. So I'll put that under this. This is a very good, this tosylate ester is a very good leaving group. He's a great leaving group. Okay? Okay, so now we did the another reaction talking about very good leaving groups. Okay, so what have we done so far? Let's come back over here. So far we've done the substitution of alcohols, we've protected the alcohols, and we did an extra reaction here just because I wanted to throw that one in where we talk about the good leaving groups. Now let's talk about some elimination of alcohols. All right, so now let's keep going. So we said we went over again where we do substitution, protection, we talked about leaving groups. Now let's go ahead and talk about one more thing, and let's talk about the elimination of alcohols. So we said before, let's have an alcohol here first off. Let's have an alcohol here. So when we do elimination of alcohols, in other words, what we're doing is we're taking that alcohol off, and what are we doing? We're going to try to form a double bond. So how does this reaction occur? Well, there's two types. We're going to do one where it only occurs on primary and secondary alcohols first. So this reaction we're going to do is only occurring on primary and secondaries only. Only occurs on primary and secondary alcohols. There's another reaction that we'll do that only does it on tertiary. It's the only one that can function on tertiary. All right, so let's go ahead and dive right in. So what we're going to do is we're going to run this in what's called POCl3. So you're going to have phosphorus here with a double bond of the oxygen, and then you're going to have 3 chlorine atoms here coming off. Okay, so what happens here? Guess what? It's the same concept over and over again. These lone pair of electrons come over, attack that phosphorus, and then this lone pair of electrons on the oxygen are going to fly up to high energy levels, and then what do we get? That's our first step of the reaction, right, or our mechanism here. And then we have oxygen bound to the hydrogen, lone pair of electrons at a positive charge, phosphorus with a lone pair of electrons there, and we already know what's going to happen with that guy. We know one of these guys are fricked, right? All right, so what happens? Remember what I said before. Who comes in and rips off that hydrogen? The pyridine. So we can run this reaction in pyridine once again. And another thing that can happen here is we can actually come over here and we can rip off that hydrogen. And we can plop those electrons onto the oxygen, right? So we plop those electrons onto the oxygen, and then what else can happen? Remember the reaction before where oxygen had these electrons up at high energy levels, doesn't like it? He's like, I'm going to come back down. So what happens? These electrons come back down to low energy levels, but then the phosphorus has to kick someone off. He's like, all right, chlorine, you're fricked, you got to go. So chlorine leaves. All right, so now chlorine leaves, so what do we have here? We removed the hydrogen, and we brought these electrons from the oxygen down and kicked off a chlorine. So now this is our structure here. Lone pair, phosphorus, double bond oxygen, and 2 chlorine atoms. Okay. Now, if you remember before, this is pretty cool. Now we know, okay, we can do something with this now. This is pretty cool because I could either have maybe something substitute or maybe this could leave. What's going to happen here is, if you remember, that pyridine can actually do something here. He can actually come in, because you're going to have more than one pyridine in this reaction. You're going to have thousands upon thousands of pyridines. There's going to be hydrogens right next to that oxygen right there. There's 2 hydrogens right there. Over here on that carbon right there, I could have oxygens, but you never want to take from this guy. So what am I going to do here? This nitrogen is going to come to the carbon over here, and he's going to rip off that hydrogen. But when he rips off this hydrogen, what's going to happen here is this bond right here that's going to break between the hydrogen is going to flop down right there. And when that happens, this whole bond right here, but with this whole oxygen, phosphorus, oxygen, chlorine molecule, is all going to pop off. And then what happens here? What do we get out of this? So if you look at this, the final product of this reaction, so this was first step, second step, third step here, we're going to have a double bond. We're going to form a double bond out of this. So that was an elimination reaction, right? And how is this elimination reaction occurring? Well, because this is occurring within, usually at the same time this is leaving and this is attacking, this is proceeding at an E2 step, right? So this is kind of like an E2 reaction, okay? So that's this mechanism. So what we're doing is, if you think about the overall reaction, what would the overall single step reaction look like? I would just take my alcohol, which could be primary, could be secondary, and what do? I react this with POCl3 and pyridine, and what's the overall result? I get a double bond. Now there is a rule that I'm going to talk about very, very briefly, just super, super quick, and it's called Zaitsev's rule. Because we'll talk about this when we talk about alkene reactions in more depth. All Zaitsev's rule says is that, pretend this was a secondary alcohol, pretend for a second. So let's actually pretend for a second I draw a secondary alcohol here. It had that whole oxygen, phosphorus, double bond, Cl molecule there, right? What that pyridine can do is, it has an option here. It can take the hydrogens here off of this carbon, because it can only take the ones adjacent to this oxygen, the carbon bound to this oxygen. I can take these. I can take one of any of these hydrogens. Which one does this pyridine want to attack? It wants to take the hydrogen adjacent to that carbon with that leaving group there that has less or fewer hydrogens. So I could have formed a double bond right there, right? But I don't want to, because that's not going to be Zaitsev's product. Zaitsev's product would be the double bond forming right here, because it's the most substituted alkene. Okay, so whenever you're doing this reaction here with the POCl3 and pyridine with an alcohol, just make sure that you're always getting Zaitsev's product by following Zaitsev's rule. Okay, let's do the next alcohol reaction where we eliminate it. And we're going to do this one, but it's only going to function on tertiary alcohols. So now let's draw a tertiary alcohol here. So there's a methyl group, I'll put a methyl group, and then we'll draw an OH there. Okay. Now what I'm going to do is I'm going to take this tertiary alcohol. Why is it called a tertiary alcohol? So if you look at alcohols real quick, if I have a carbon bound to an alcohol here and it's bound to 3 carbons, that's a tertiary alcohol. If it's only bound to 2 carbons, it's a secondary alcohol. If it's only bound to 1 carbon and everything else is hydrogens, it is a primary alcohol. Okay? So this is a tertiary alcohol, because if you look here, it's bound to 1, 2, 3 carbons, and then the alcohol. All right. So we're going to react this guy with hydronium. Hydronium is basically an acid, right? So it's a weak acid. And what hydronium can do is, it's going to be a very good electrophile. Because you know nucleophiles are going to be basically acting as bases and they have negatively charged centers, whereas electrophiles are going to be a little bit more of acidic in form, and they're going to be having specifically positive charges, and they're going to be good electrophiles. So this oxygen, he's going to come over and he's going to take that hydrogen there. He's like, that's mine. Rips that hydrogen off. What happens then? This bond right here breaks on to that oxygen right there. And then what do you get out of this? Then in your first step here, we have oxygen, which has these 2 hydrogens with a lone pair of electrons plus charge. It's the same thing, right? Just instead of it being all this other stuff over here, now it's just a hydrogen. And then we should have a methyl group right there. Now, what do? We actually formed water out of this process, because we ripped off a hydrogen off of hydronium. So hydronium is the acid, and this is basically our conjugate base in this form. Well, if he's a base, then he's going to be able to act as a nucleophile in this case. So what does he do? All right, he looks over here and he says, all right, there's 3 hydrogens over here. There's 2 hydrogens over here, and then there's 3 hydrogens over here, but this wouldn't be a good one. Okay, what could I do here? So water says, I got my pick. I can come over here and take a hydrogen from this group of 3. I can come over here and take a hydrogen from this group of 3, or I can come and take a hydrogen from this group of 2. But remember what we said? Zaitsev's rule. Zaitsev's rule says take the hydrogen adjacent to the carbon bound to this oxonium ion who has fewer number of hydrogens. So this one has 3, 3, and 2. That's the fewest one. I'm going to take that one. So what does he do? He comes over, rips on that hydrogen, and what happens to this bond of hydrogen? It flips onto that carbon right there, forms a double bond right there. But at the same time it does that, this guy right here is going to have to leave. But I should be even more specific here. So what I'm going to do is, to be even more specific, because this reaction doesn't necessarily proceed in what's called an E2 fashion. It actually proceeds in what's called an E1 fashion. So really what should have happened here is I should actually say that oxonium ion that you have there, he should leave first. And then after he leaves, what do we have? We have a carbocation. And then he would have had those choices of hydrogens, right? And then specifically he would come in, pick the one with the fewer number of hydrogens, put that bond right there, and then make a double bond. So specifically, this should proceed, if we were to be very, very specific, this reaction should proceed in what's called a E1 fashion. And the reason why is because you have such some steric hindrance here. Because of this actual methyl group, it might interfere with the nucleophile trying to come in and rip off that hydrogen. So there could be a little bit. So again, this would prefer to proceed in more of an actual E1 fashion. All right, so that's that right there. But again, E1, E2 for the specifics of this mechanism isn't super important, but just know that it should form a carbocation first, and then the water should come and attack. So again, what would the single step reaction of this look like? You would just have a tertiary alcohol, and the overall result when you react this with hydronium. Oh, and you want to react this with something that's going to be polar aprotic. So you'd want to react this with tetrahydrofuran, okay? So you want to react this with tetrahydrofuran in this case. Okay? All right. And then what would be the result? If you react this in tetrahydrofuran, which is THF, denoted like that, you're going to get an alkene, but a tertiary alkene. I should have put that there. Sorry about that, and that there. Okay, and that there. All right, so now you should have boom, boom. Okay, so that should be the result of our single step reaction. Sorry about the methyls, guys, but I should have kept my methyls flowing within this. All right, so that is the acid catalyzed reaction here, where we're turning an alcohol into a alkene following Zaitsev's rule, but this one only occurs on tertiary alcohols. Okay, so what have we done so far? Let's come back over here. We've just finished the elimination of alcohols. Next thing we're going to do is we're going to go right into the oxidation of alcohols. All right, so let's continue, guys. So let's continue going. We were from elimination of alcohols. Now we're going to go into the oxidation of alcohols. All right, so oxidation of alcohols. Well, first off, before I even go into those reactions, what is happening with an oxidation reaction? So oxidation reaction, we can actually think about this as you're going from specifically a low priority functional group, so a low priority functional group. For example, the one we're going to talk about we're starting with is a hydroxyl group, right? So an OH. Let's just put ROH here. And you're turning this into a high priority functional group. And what do I mean by priority functional group? If you remember your hierarchy of your functional groups, it can give you a very important tool to be able to remember this. So alcohols are a little lower than the functional groups as compared to aldehydes. Okay, so that's one that we're going to talk about here. Or converting this alcohol into a ketone, and we'll talk about that reaction. Or converting this alcohol all the way into a carboxylic acid, and we'll go over that reaction too. So again, before I start getting into these, specifically remember that going from a low priority functional group to a high priority functional group is the definition of oxidation. All right, or we can also remember that the biological / chemistry definition of oxidation is the removal of hydrogens or the removal of electrons and the gaining of oxygens, right? So that's the overall concept here, okay? All right, so let's go ahead and dive into this. So first reaction we're going to get into here is we're going to talk about turning an alcohol into an aldehyde first. But the mechanism for forming a ketone is going to be the same thing, all right? So we're only going to do the one mechanism that would apply to both scenarios. All right, so let's say, hey, we take here, again, we do a primary alcohol. And this reaction, we can run it on a primary alcohol or a secondary alcohol. We're only going to do this one specifically on a primary. All right, so we have to have here pyridinium chlorochromate. So Cr, double bond oxygen, and then we got an O negative over here, double bond oxygen right there, and then we'll have a Cl there. So we have pyridinium chlorochromate here. So this is our pyridinium chlorochromate. What happens with this reaction? Same thing as we've talked about over and over and over again, right? The oxygen right here, the lone pair of electrons on the oxygen comes over and attacks that chromium, the central atom, right? The chromium. Then what happens? These pi electrons come up onto the oxygen, and what happens here for this first step here? What do we get here? We have our oxygen, lone pair of electrons bound to the hydrogen, plus charge. See that thing over and over again. Oxygen with a negative charge there, other oxygen with another negative charge. Then we got the double bond oxygen right there, and then we have our chlorine. But as we've seen over and over again, what happens? The pyridine, we can have pyridine in this reaction. We see him over and over again, right? He comes in, rips off that hydrogen, bond breaks off into this guy. What else happens? Lone pair of electrons on the oxygen flips down right there. But then if he comes down, chromium's like, all right, someone's got to leave. Chlorine, you're better than everybody else. You leave. So then chlorine leaves. And then what's the overall, what's it going to look like afterwards? So we're going to have here the oxygen, who's going to be having the two lone pair of electrons, bound to the chromium. This guy turned into double bond oxygen. This guy's still oxygen with a negative charge. And over here, we're going to have another double bond oxygen. So same structures we've been seeing over and over again. Now what happens? Okay. Over here, I have a hydrogen sticking right there, right? So I got a hydrogen just hanging out right there. Guess who's coming back again? Guess who's back? Back again. The pyridine. Pyridine's back. So what does pyridine do? Pyridine comes in here and attacks that hydrogen. When he attacks that hydrogen, this bond right here flips right there to form a double bond. And then when that happens, this bond between the oxygen and the chromium breaks off. I'm sorry. This will break off right here. That bond will break off. And when that breaks off, look what we get here then. So then after that, we will have carbon, who was just bound to a single bond oxygen, and hydrogen is now going to be doubly bounded to the oxygen. And also would have one other hydrogen right there. So it's going to have one hydrogen right there. And what's the other inorganic product that we get out of this? Double bond oxygen. Then we'll have this guy with the negative charge, and then we'll have the double bond oxygen there. He'll have the lone pair, and he'll probably go and recapture maybe that chlorine again, right? So this is our product here. What did we get out of this? We got an aldehyde. So we took a primary alcohol and converted it all the way into an aldehyde. That's important because if we run this reaction in pyridinium chlorochromate in a secondary alcohol, guess what else we'd get? So if I ran this reaction here, I'm not going to go through the whole mechanism. It's going to be the same concept though. Everything that we did is going to fall in the same flow. If I took this secondary alcohol and I reacted him with pyridinium chlorochromate and pyridine, we actually shorten it as PCC, pyridinium chlorochromate, I could convert this right into a ketone. And that would be my reaction. So in a single step reaction, what would these two reactions look like? Well, it would look generally, this would be the secondary alcohol conversion into a ketone. So secondary alcohol, if I run this with PCC, it'll convert it into a ketone. If I run this reaction of a primary alcohol and I run it with PCC and pyridine, what do I get out of this? I get a aldehyde. And that is basically summing up the oxidation of an alcohol, specifically using pyridinium chlorochromate, right? Well, there's one more that we could actually do. And this one's a behemoth of one. All right, so we did the oxidation of primary and secondary alcohols. Now let's do the oxidation of a primary secondary alcohol from an alcohol all the way to a carboxylic acid. All right, so remember, this mechanism, we're just repeating it another time. So let's go ahead and blast through this really quick then. So we can actually get up to this point of where we have an aldehyde. Actually, let's just start there. So pretend we're going to use a different reagent though, but it's going to be the same steps here that we just went through. So we can just start with this aldehyde right now, but we're going to use a different reagent, okay? So we're going to start off with let's say we start off here with a primary alcohol, because you need to start off with a primary alcohol for this reaction to occur. So this reaction can't occur on secondary alcohols. I'm sorry, it only can occur on primary because we want to turn it into a carboxylic acid. So if we take this primary alcohol and we react this primary alcohol with, we're going to react this with chromic acid, so H2CrO4. You can also react this with, there's multiple reagents. You could use this, you could use the actual you can use chromate with the acid. You could use sodium dichromate, okay? A lot of different substances you can use here, but in general, we're going to use chromic acid, okay? And what's going to happen? Well, if you remember before, we're going to start off with the aldehyde. So we're going to continue where we converted into the aldehyde first, because it's the same mechanism here, same exact mechanism that we did when we talked about pyridinium chlorochromate. But now we're just going to continue off with the aldehyde and show it how it gets converted into a carboxylic acid. So let's draw our chromic acid. The only difference here is that it's just going to have OHs there, and then double bond oxygen right there. Okay, what happens? First thing, before we even react this guy with the chromic acid, we have to react it with water. So we're going to react this first with water. So we're going to take water, and what water is going to do is it's going to see that carbon right there, and it's going to be like, that carbon look good, all right? Why? Because these lone pair of electrons on that oxygen are pulling, because of the electronegativity difference, it's pulling the electrons away from the carbon. So it's a partially positive carbon. And he's like, So he comes in and attacks that carbon. When he comes in and attacks that carbon, what happens? The pi electrons come up onto the oxygen. And then look what you get out of this. That was the first step. We're just assuming that we start off with the aldehyde here. So the second step we did is we reacted with alcohol. Then what? We have oxygen here, these lone pair of electrons. And what else do we have over here? We also have that OH2 that we added, right? The water. And then we have another hydrogen here. Well, these lone pair of electrons in the oxygen, they come over and attack that hydrogen, and that bond flips on there. Now what do we have? Now we have a diol, if you will, right? So we have an alcohol here and an alcohol there. And then we have a hydrogen. Then what happens? Now we react it with the chromic acid. So now what we're going to do is we're going to take this guy and we're going to react with him. What happens? So what we do is we take that Cr double bond OH there, double bond oxygen there. These lone pair of electrons on the oxygen come in and attack that chromium. When it attacks that chromium right there, these lone pair of electrons come up. But we're going to skip this step because we already know what happens. When he comes up, right, then what happens again? He'll actually come back down and kick off the OH. So let's say that he comes up and then what? Comes right back down. And what's the result of that? It kicks off the OH, if you remember from all these previous reactions we've done, right? And what is that going to look like now? Now we're going to have this oxygen, who is bound to a hydrogen, plus charge here, right? And if you remember what else happens within this reaction where it comes up, comes back down, OH leaves, the pyridine, right? Remember the pyridine? He's always there. He comes in and rips off that hydrogen, right? So that hydrogen's going to be gone there. And what do you have here? You have oxygen, which is bound to chromium, double bond oxygen, OH, double bond oxygen right there, the OH left, right? And then you also have the other OH here. And then you have that other hydrogen. Now what happens? That OH that we kicked off, he's pissed. He's like, you do that to me? No one does that to me. I'm coming back and I'm taking what's mine, and I'm taking this hydrogen here. So he says, I'm going to take this hydrogen. Well, guess what this bond between the hydrogen does? It flips up right there. Right between this bond between the oxygen, the hydrogen, the oxygen, the carbon, right? Flips right in there. And then this whole beast of a thing over here that we have over here, see this whole chromium thing that we had over there? It's all going to break off. So here we have these lone pair of electrons right there. Actually, I'm sorry, these arrows shouldn't go there. The arrow should actually go right there between the carbon and the oxygen with the chromic acid, right? So again, I'm sorry about that. The hydroxide should come in and attack that hydrogen. And when it attacks that hydrogen, the bond should actually go on to the oxygen that's bound to the chromic acid. And then when that happens, this bond between the oxygen and the chromium breaks off. And then what do we get as a result of this? So again, this was step 2, step 3, step 4, and step 5, we'll finally have our finished product here. And what will that look like? Double bond to the oxygen, and then the single bond to the OH there. Okay, so it's a beautiful thing, and what have we done? We formed our carboxylic acid. So we formed our carboxylic acid. So this is important to remember this. So what's the overall single-step reaction going to look like in this? We would take our primary alcohol. So remember, it has to be a primary alcohol. You can react this with H2CrO4. What else could you do? There's other things. It's not just that. You could react this with CrO3 and acid. You could react this with sodium dichromate. So there's a lot of other things that you can do with this alcohol as reagent-wise, but we just did chromic acid. But again, these two could provide the same product. And the overall, and you react it with pyridine, the overall product of this was a carboxylic acid. And again, how did it do it? It converts it into an aldehyde, and then after it converts it into an aldehyde, it converts it into a carboxylic acid. So it's a beautiful thing. So again, what have we done so far? We've done a lot so far, guys. We've done substitution, protection, elimination, and we just finished the oxidation of alcohols, where we did primary and secondary alcohols with PCC to form ketones or aldehydes, and we did their mechanisms. And then we did an oxidation of a primary alcohol, following the exact same mechanism where we'd actually convert it into an aldehyde. We then continued using chromic acid, or you can use this CrO3 and acid or the sodium dichromate, and then throughout all of that, you produce a carboxylic acid. All right, guys, so now what we're going to do is we're going to pick up the rest of the alcohol, ether, and epoxide reactions. We're going to start off with quinone synthesis. So if you want, guys, go ahead and click up in the right corner there, click on the quinone synthesis, and we'll see you in the next video.